Hello everyone, welcome to this lesson on electronic transition in UV visible spectroscopy 200 to 800 nanometer. UV visible spectroscopy is used to analyze the chemical properties of a material. It can be used to determine concentrations, identify unknown compounds, and provide information about the physical and electronic structures of organic and inorganic compounds. Electronic transition in the context of instrumental methods of analysis refers to the movement of electrons within a molecule from one energy level to another in response to the absorption or emission of electronic radiation. A molecule absorbs a specific quantum of energy like a photon of light. Electrons can be promoted from their stable or ground state to a higher energy or excited state. The ultraviolet region falls in the range between 200 to 400 nanometer, while the visible region falls between 400 to 800 nanometer. We also have the far UV region that falls below 200 nanometer. Sit down and listen to the rest of this lecture. Don't forget to subscribe, like, comment, and share this video. One thing I know is that it's your subscription that keeps me going. Don't forget to subscribe. Please subscribe, like, comment, and share this video. Objective of the study. By the end of this lesson, the student is expected to understand what electronic transitions are, to understand the term used in UV and visible spectroscopy, to be able to explain the types of electronic transitions and solve some problems on electronic transitions in UV visible spectroscopy. Electronic transitions. We say that electronic transitions occur in terms of atoms and molecules due to the absorption or emission of electromagnetic radiation, typically UV or visible. The energy change associated with a transition is related to the frequency and wavelength electromagnetic wave by Planck's equation E equals to hv. When electromagnetic transition or electromagnetic waves on an atom or molecule is supplied with energy in the form of a photon, the electrons get excited and jump from one energy level to the other. Looking at this figure 1, these electrons absorb the energy from these photons and they jump, as I said, from one electron shell or orbital known as energy level to another. The first lower energy level is what we call the ground state, energy level. And the second higher level is the excited state. The second electron shell is a much higher energy level than the first. Each electron shell has a fixed energy level. The analytical technique or spectroscopy to plot a graph of the light absorbed by an atom molecule or solution, separating the light waves by their wavelength. This graph is known as a spectrum, used to work out the energy absorbed by the atom, molecule, or solution, and deduce the electronic transitions that take place. What happens when electromagnetic radiation is applied to a molecule? When we apply electromagnetic radiation to a molecule, as shown in figure 2, electron transition from lower energy to higher states will occur. This can be in the form of electronic transition, rotational transition, or vibrational transitions. In electronic transition, molecules move from ground state to excited state. In rotational transition, Molecules rotate clockwise or anti-clockwise, and in vibrational transition, they can stretch or bend, which is common in infrared spectroscopy. Vibrational energy as chemical bonds are not fixed, but flexible. So, bond length may increase or decrease, and bond angles may be modified. What are the terms used in UVV spectroscopy? In UVV spectroscopy, we have some terms like the chromophores. These are groups of atoms responsible for UVV's spectroscopic absorption. They have double bonds, such as ethene, butadienes, carbonic compounds, aromatic rays, etc. We also have the oxochrome. The oxochrome are substances that increase the absorption of a molecule, such as methyl, hydroxyl, alkoxyl, or amino acid groups, or an atom of halogen. In pi electron systems, an oxochrome will shift the lambda mass value to a longer wavelength, known as the bathochromic effect or redshift. We also have the hypsochromic effect, called the blue shift. This is a shift to shorter wavelength. We hear of hyperchromic effect, which is an increase in absorption towards higher absorbance. We also hear about the hypochromic decrease or the hypochromic effect, which is a decrease in absorption towards lower absorbance. What happens, or what are the types of electronic transitions? From this figure, we are going to observe the different types of electronic transition. When it comes to electronic transition, electrons always jump, as we say, from bonding or non-bonding to anti-bonding orbitals. The bonding and anti-bonding orbitals form the ground state. From the figure we have here, we can see the first state is the sigma bonding, the second state is the pi bonding, and then the third state is the M bonding orbitals. So these three form the ground state, and they get excited and they move to the anti-bonding orbitals, where we have the pi star anti-bonding orbitals and then the sigma star anti-bonding orbitals. So four distinct types of electronic transitions are formed. One, we have the pi to pi star transition. We have the sigma to sigma star transition. We have the N to sigma star transition, and then we'll have the N to pi star transitions. We have what we call forbidden transitions, which are sigma to sigma star forbidden transitions, and then we'll have the pi to sigma star forbidden transitions. Each of these transitions, that is the allowed transitions, we will look at them separately. The ultraviolet region falls in the range between 200, some people say 190 to 380, and some book takes it as 380 to 750 nanometers. The sigma to sigma star transition, how does it occur? In this transition, the molecule or the electrons in a molecule move from a bonding sigma orbital known as HOMO. HOMO is highest occupied molecular orbital, and then to an anti-bonding orbital, sigma star, referred as the LUMO, lowest unoccupied molecular orbital. This transition takes place due to the electromagnetic radiation that gets absorbed, and the energy used to jump from one of the electrons from the HOMO to the LUMO is referred to as sigma to sigma star transitions. This transition requires a large amount of energy, so they typically occur in the far UV region. Examples of compounds that show sigma to sigma star transitions are saturated hydrocarbons like methane, ethane, hydrogen molecule, cyclohexanes. They occur in the far UV region and can be used as a solvent in ultraviolet spectroscopy as it absorbs around 180 nanometer and will not affect the radiation in the UV region of 200 to 800 nanometer. So in ethane and cyclohexane, we'll have the structure here, and then we can see the carbon-carbon sigma bond. We can also see the carbon-hydrogen sigma bond. So in a compound like this, sigma to sigma star transition can occur. Pi to pi star transitions. We have an example, ethene, 1,3-butadiene and 1,3,5-hexatriene. We also have benzene as an example here. Here, an electron transition from a bonding pi orbital to an anti-bonding pi star orbital. These are observed for compounds that have conjugated double bonds, like the ethene, 1,3-butadiene, benzene, and 1,3,5-hexatriene. Ethene absorbs at 175 nanometer. 1,3-butadiene, hexane, and 1,3,5-hexadiene show color in the visible region greater than 200 nanometer. They act as what we call chromophores, responsible for UV visible absorption of the molecule. They have carbon double bonds. They have conjugation, different types of carbon double bonds. They also have aromatic structure in them, especially in benzene. Aromatic structures have these pi to pi star transitions. What are the effects of conjugation? When you have a compound that is highly conjugated, the absorption peak is shifted to a shorter or longer wavelength. Lower energy is required when two or more chromophores are conjugated. An increase in the number of conjugated bonds leads to absorption of visible light, and compounds will be colored. In this type of pi-pi transitions, we know that ethene has only one double bond there, so it will absorb at 175 nanometer. That is in the far UV region. Molecular picture to that of ethene and 1,3,5-hexatriene. If we compare the molecular picture of ethene and 1,3,5-hexatriene, we will find that from this molecular picture that ethene absorbs UV light at 165 nanometer, while 1,3,5-hexatriene absorbs at 258 nanometer. So we know that conjugation increases the energy of the HOMO and decreases the energy of the LUMO for conjugated system. When a double bonded molecule such as ethene absorbs light, it undergoes a pi-pi transition because of the double bonds. Because pi-pi transitions energy gap are narrower than sigma-sigma pi transition, ethene absorbs light at 165 nanometer, a longer wavelength than molecular hydrogen at 111 nanometer. The increased conjugation as we can see in that figure, in 135 hexatrine leads to what we call a bathochromic shift, a red shift, moving the absorption maximum to longer wavelength. You can see the wavelength that 135 hexatrine is having there, 258 nanometer. As conjugated pi systems become larger, the energy gap for a pi-pi transition become increasingly narrower, and the wavelength of light absorbed correspondingly becomes larger. The absorbance due to the pi-pi transitions in 135 hexatrine, for example, occur at 258 nanometer, corresponding to a delta E of 111 kilocal per mole. And you can also see that the energy gap between the HUMO and the LUMO is shortened when you compare it to the energy gap of ethane. The energy gap in ethane is wider, while the energy gap in 135 hexatrine is longer because of the increased conjugation in this compound. N to sigma star transitions. In N to sigma star transitions, electronic transitions occur when non-bonding electrons are excited to the sigma star anti-bonding orbitals. It is possible in saturated compounds with lone pairs of electrons, such as oxygen, nitrogen, sulfur, fluorine, chlorine. It also occurs in saturated halides, alcohols, ketone, and amines. All of these compounds participate in N to sigma star transitions. Like sigma to sigma star transition, N to sigma star transition occur in the deep UV region. It absorbs light less than 200 nanometer and can be used also as solvents in the UVV region. N to sigma star transition has less energy compared to sigma to sigma star transitions. N to sigma star transition is one of the most common transitions in organic molecules. Also, transitions that occur in organic molecules are N to pi star transitions and pi to pi star transitions. If we look at the example of dimethyl ether here, it has two methyl groups attached to an oxygen group. So in dimethyl ether, we will have the N electrons because the oxygen group there has lone pairs of electrons. We have the N electrons. So we are expected to have also the carbon-oxygen sigma bond and the carbon-hydrogen sigma bond. Another example is the ethanol as shown. The ethanol will have the carbon-carbon sigma bond. We will have the carbon-hydrogen sigma bond. We have the carbon-oxygen sigma bond. And then we will have the N electrons because of the lone pairs of electrons there. And then we also have the acetaldehyde. In acetaldehyde, we have the carbon-carbon sigma bond. We have the carbon-hydrogen sigma bond. We have the carbon-oxygen sigma bond. And then we'll have the carbon-oxygen double bond. So we'll have pi electrons there. And then we'll have the N electrons. So acetaldehyde has both sigma, pi, and N electrons in it. Another transition is the N to pi star electronic transitions. In N to pi star electronic transition, an electron in an unshared pair or a heteroatom is excited to pi star antibonding orbital. It involves the least amount of energy of all types of transition. In ultraviolet UV spectroscopy, the N to pi star transition gives the absorption with a longer wavelength. They occur in at longer wavelength closer to the UV visible region. Halogens and elements like sulfur, oxygen, or nitrogen display this type of transitions. A classic example would be the carbonyl group, carbon to oxygen double bond. An electron from a non-bonding orbital will transition to an anti-bonding pi star orbital. These groups, such as ketones, aldehydes, absorb in the 270 to 300 nanometer range. Characteristics of N to pi transitions. They have molar absorptivities that are usually less than 2000. They undergo a blue shift when interacting with solvent. This is because the lone pair of electrons interact with the solvent, causing the energy of the transition to increase. They are considered symmetry forbidding or overlap forbidding because the electron is promoted from the molecule's plane to a perpendicular plane. We have come to the end of this lecture and we'll be looking at some questions. We are expected to list question 1. List the 4 distinct types of electronic transitions. Define HOMO and LUMO. Question 3. Explain the following terms: auxochrome, chromophore, and bathochromic shift. Identify the different types of electronic transitions in the following compounds: ethane, hydrogen, ethene, ethanol, acetaldehyde, and acetone. When you identify them, try to know the types of transition that can occur in them. The type of, whether it's sigma-sigma transition, pi-pi transition, N to pi star transition, N to sigma star transition. Identify. These are the questions that are very difficult for students. Learn this lesson. It will benefit you. Thank you for listening. Thank you as we have come to the end of this lesson. Don't forget to subscribe, like, comment, and share. Subscribe, like, comment, and share. Thank you very much.